So last time we gave an inductive proof for the Pick theorem. The Pick theorem is a theorem about interpolation of points from the complex unit disk to the complex unit disk. And what we showed was that if you have a certain matrix that is positive semi-definite, then what you can do is you can interpolate a collection of points such that the largest value of a function that interpolates those points remains bounded by 1 in norm. So the proof was inductive. And so what we did is we showed we can interpolate exactly 1 point if and only if this 1 by 1 matrix was positive semi-definite. So then we take n points that can't be interpolated, and what we did is we had this algorithm where we shifted the last point to 0 in both the input and the output, so we get a new function that sends 0 to 0. And then in order to remove that last 0 to 0 interpolation point, we just divided by z. And so the way that this theorem works is you take these n points that you want to interpolate, and then you reduce it to n minus 1 to n minus 2 all the way down to 1. And then you have this 1 point, and you know that's interpolatable if and only if this matrix is positive semi-definite, and this is a 1 by 1 matrix, and then you build back up with another algorithm for the matrices. And so what I'm really concerned with here is the interpolation problem itself. And they say that you don't really know a theorem until you can code it up, and so why don't we go ahead and do it. So the first thing we need to do is collect our points. What I'm going to do is I'm going to make a figure, plot a circle so I know where I should click in, then I'm going to use the get points command in MATLAB, and that'll get me the points for my input, and then I'll also get points for my output. Okay, so I just got that done, and so now what I'm going to do is I'm going to click, click, and then double click to end, right? And so now we have in our X and Y, we have our points. So press X, and I press Y, there we go. So these are the real parts of my points, and these are imaginary parts of my points. So I go ahead and I put them into what I call input points, and input points takes my real points and it adds square root minus 1 times my imaginary points. I use square root of minus 1 rather than I because I often use I as the index variable, so I don't want to confuse that later. This gives me my inputs, so we can also get our outputs the same way. What we need to see next is if these points are actually interpolatable. So let's go ahead and make that matrix we saw earlier. So what we're doing here is we're actually using the Pick theorem. And so I'm taking a look at this matrix that we made here. And this comes from the output points and the input points. If the smallest eigenvalue of this is negative, and we know they're all at least real because this is self-adjoint matrix, the Pick theorem tells us that these can't be interpolated. So we're just going to say it's not going to work, right? So collecting my input points, so here. Now let's collect larger points here. And it tells us it's not going to work. Now that makes a lot of sense, really, because if you are going from smaller points and interpolating to larger points, then there might be another point where you have sort of rippled out and exceeded 1, and that's exactly what's happening here. Most of the time when I do this, I'm going to actually be taking a larger collection of points and setting it to a smaller collection of points. And then you see, it says let's do this because it works. Now let's go ahead and see if we can code up a 1-point interpolation problem. So what I've just done is I made 2 Blaschke functions. And so one will send z0 to 0, which is our input, and the other one sends w0 to 0. What I really want is I want to send z0 to w0. What I'm going to do is I'm going to actually compose these 2 guys. Right, and that should be my Blaschke factor, except I haven't inverted any of these yet. What you can see here is that if I take the first Blaschke function and I put in z0, that's going to send me to 0. So what I want the outer one to send me to w0. And so I'm going to invert this Blaschke function, and these are super easy to invert. All you need to do is flip the sign here. And that's all we need to do. So now let's go ahead and make a quick plot routine, and that'll be our first example. Okay. So this is what I just did. I'm going to basically be plotting around the circle. I want to cover the entire unit circle, so I'm just going to do a square going from -1 to 1. And if you look here, I have basically made an X plot and a Y plot out of the mesh grid command. And then I made a Z plot that is the same size as X plot. And then I just run through all of the I's and J's going from 1 to the length of X, and I fill in Z plot with our new function evaluated at these points. So then what I do is I take a surface plot of these guys, and yeah, that's done. So that should give us our first point, and let's just make sure the point is actually on there. And so I'm going to use the plot3 command. So I'm going to use the plot3 command, and I take the real parts of my imaginary inputs, so those are my x's, the imaginary parts for my inputs, and those are my y's, and then I'm just looking at the absolute value of these guys. So I'm not looking at, it's a two-dimensional output if you think of it in terms of real variables. So I'm just going to plot the absolute values and we'll call it there. We can go and check with the actual interpolated values to make sure it actually works. But let's go ahead and take a look. Input point, output point, see what we get. Boom. Oh man. So we see that this guy is extremely large and that's really bad. So this is going up to 70, but you'll notice this is actually outside of our unit circle. And so what we're going to do is we're going to go ahead and we're going to zero out anything outside the unit circle, because the poles of these Blaschke functions sit outside the unit circle, and the closer the zero is of the Blaschke function to the boundary, the closer the pole itself is going to be to the boundary. What I'm going to do here then is I'm going to tell it to plot the minimum between 1 and the magnitude of the z-plot. So that should take care of that. Let's try one more time. And so it should look flat on the outside. Boop. 1 point for input, 1 point for output. There we go. And right there on the surface. So we see that we are sitting exactly where it is, at least in magnitude. Now we need to make sure it actually is doing what we think it is, and so I'll take a look at g applied to the input points and subtract the output points. And it's a flat 0. So we interpolated a point successfully. Now, let's see if we can add in more points. In order to do this, we're going to have to go ahead and apply that transformation. And so essentially all the points get shifted each time, and they get shifted by sort of Blaschke transformation. So we're going to take a matrix and we're going to make this matrix that is going to be reducing by 1 point as we go down. It's going to be non-zero on the upper left hand side of the matrix, and it's going to be completely zero on the bottom right half. So let's go ahead and do that. Shouldn't take too long. Okay. So what I have done is I just set up two matrices. These are now matrices consisting of entirely zeros, and one is our input transformations and the others are output transformations. If you take a look at this, I made it so that this is a square matrix where each side length is the length of the number of inputs. Now the first row really just needs to be the inputs themselves. So I'm just going to go ahead and take this. First row taken care of. Now for each successive row, what I'm going to do is I'm going to take that last point on the previous row, and then I'm going to go ahead and transform them. I'm going to send all the zj's to zj minus zn divided by 1 minus zn bar zj, and that'll give it my second row. And then for the next row, I'm going to be subtracting off zn minus 1, and etc. So let's go ahead and do that. Okay, so I've made that transformation here, and you can read it right here. Now, I also made the transformation to the output, because it's the same sort of deal. But now what we need to do to the output is we now need to also divide by our new input points. So I'm going to do that one at a time as well. Okay, so that's all the transformations for our inputs and our outputs. Let's go ahead and click some points. So here's a 1, 2, 3, and 1, 2, 3. And so you can see exactly what these matrices look like. So I'm going to have the input transformations, and it looks like I actually have an error. Let's see. I think I'm not going quite far enough here. Okay, so let's give this a try again. So 1, 2, 3, 1, 2, 3. Now, those points are completely off, and that's okay. We haven't made the interpolation yet. We see that this is a matrix that has 3 entries on the top, 2 entries in the next, and 1 entry here, and everything else is 0. And so that is exactly what we want, and so good. So then the point I want to actually interpolate then is I want to put in here these points where I take a look at the last row and the first column. And that is going to be the first point we interpolate, and then we're going to build back up. That's our first function. And now let's go ahead and make our recursive routine that will take us from that first point to all the points otherwise. Okay, so what I'm going to be doing is I'm going to start at the bottom, and we're going to go 1 up from the bottom. Then what we're going to do is I'm going to undo that whole division by z by multiplying by z. It's important also that we put the period here before the multiplication, because that means we can put in a whole vector of complex values and it'll be able to evaluate it. Now we multiply by that z. Now we need to do that transformation that undoes everything. So if you remember, what we did to get from F to G was we did this transformation here. Now we want to undo that transformation, which means that we're going to invert the outside and then invert the inside. This is how it goes. We still need to figure out what Wn is, but this is our output. Before, we were setting 0 to 0. So now, if I put 0 into G, we know that's going to be 0. And then this is going to end up giving us Wn. Now we want to change that 0 to be Rzn. Okay, now when we put z in here, that's going to get sent to 0. So then for the old function, that means that 0 is sent to 0, and then that means that zn must be sent to wn, which is good. It's exactly what we wanted. So now we need to figure out what zn and wn should be. We should be looking at the current row that we're on, and we should be looking at the last non-zero entry. So we're looking at the ith row of our input transformation matrix. If we are at point I, then we need to go over, not quite I, but I think the input point's minus I, something close to like. Should be something like that. Okay, that should be it. So essentially, we know that if we are at the first row, then we should be looking at the very end, and that's going to be the length of the input points. And so if I was 1, then I minus 1 is 0, and so we're going to look at the last entry here. And if we were at the last entry here at the very bottom row, then we should be looking at the point that is given 1. And so then if I is equal to the length of the input points, then this whole thing just becomes 1. So that works exactly how we want it to. And now we do the outputs as well. This should be the whole thing. And so assuming I didn't make any mistakes, let's go ahead and push play and see what happens. All right, so collecting my points, 1, 2, 3, 4, I guess. And 1, 2, 3, 4, and double clicking on that last entry. And there we go. So you see, all the points are perfectly interpolated, or at least their absolute values are. And this is a Blaschke product. So none of the entries on the inside go above 1, and that's good. And we flatten the outside because otherwise we'll have some infinities that we won't like. So this is good. This is pick interpolation all coded up. So hopefully this helps you understand how the theorem works a little bit better. And if you want to guarantee that this is actually working, what we can do is we can go ahead and take a look at the input points and the output points. Now you'll see here these are non-zero, but then again, these all are multiplied by 10 to the minus 15. So this is very, very close to 0, and so it's some sort of numerical rounding errors that have really led to this. So that's pick interpolation. It ended up working out really well. Thank you for watching, and if you do actually like the video, then I encourage you to go and boop the like button. It tells YouTube that people like it, and hopefully it means that it shares it to a broader audience. And if you want to see more about the pick theorem, then go ahead and check out this video where I go through the entire proof.